Okay, I did the time extension thing there, so we're all set. Let's see. Okay, first of all, I just wanted to say, Robert, I'm sorry because at last lecture I mislocated you in the greater LA and SoCal. I know you're from San Mateo, Burlingame, one of those places, you know, near the San Mateo Bridge, so sorry about that. Didn't mean to place you in Southern California. But anyway, are there any questions before we start? Questions? George? Good question. Okay, so why am I lecturing on Saturday night? Oh, well, the easy answer is I guess I have no life, but that's only part of the answer. The rest of the answer is that the governor of New York State has given an order that starting tomorrow, Sunday night at 8 o'clock, people's businesses have to close unless they're essential services, blah, blah, blah. And the way that the Cornell provost has interpreted that with regard to classrooms and teachers and stuff is that we're not allowed to use any on-campus facilities to deliver our courses unless we get a waiver and it's absolutely necessary and blah, 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 blah. And for most people that means you're going to have to do it from home. Now, honestly, I don't know how I would do this from home or anything even approximating it from home, given the available technology, etc. So I've appealed for a waiver of that. But for now, what I want to make sure to do is get at least 4 or 5 lectures in the can before that axe falls, because who knows how long it's going to last. Maybe it'll only last a week and a half or 2 weeks. And so you'll at least have something to watch while this is all getting sorted out. Okay, so anyway, what were we talking about last time? We were talking about frequency responses of causal LTI systems, and the bulk of the class, actually causal FIR systems, getting a little ahead of myself here, and the bulk of the class was a few examples, a few really important examples, something we call the low-pass filter, something called a high-pass filter, and then the L-fold running summer, so some what I call crucial examples that we saw. And all of these crucial examples, at the very end of class last time, we noted the following fact. So for each of these examples, the frequency response took on this special form h hat of omega hat equals a of omega hat times e to the minus j alpha omega hat plus beta, where a of omega hat is real valued. And so remember for the for the high pass filter, a of omega hat was 2 sine of omega hat over 2. For the low pass, it was 2 times 1 plus cosine omega hat. And then for the L-fold running summer, it was the Dirichlet thing. Anyway, so is real valued, and alpha and beta are both real. Okay, so the terminology here, the name for a system whose frequency response takes that form is a generalized linear phase system. So a system whose frequency response takes that form is said to have generalized linear phase, GLP. Now, why do we say it has generalized linear phase? Well, the nominal phase, the phase before we take into account the omega hat values for which the A of omega hat is negative. So here's the reasoning. The quote-unquote, what I called last time, the nominal phase, alpha omega hat plus beta, is linear in omega hat. or at least affine. What is the difference between linear and affine? Does anybody know? Does anybody know why I wouldn't want to really call alpha omega hat plus beta linear? I'd rather call it affine. Critique? Yeah, it's the beta. Like, linear would just be alpha omega hat. If you add alpha omega hat plus a constant, you get a form that's called an affine form in omega hat. And when we take into account the sign of A of omega hat, we get something that's piecewise linear or piecewise affine in omega hat. So getting the true phase of H hat omega hat, the answer comes out to be piecewise linear, or if you will, affine. And remember the pictures we had last time? Like one of them had just a line, one of them had two lines, one of them had a bunch of lines, depending on the value at L for the L-fold running summer. That's what I mean by piecewise linear or affine. Okay, so that's why we call these things, they have generalized linear phase. It's not quite linear, but it's kind of linear. Now there's a whole theory of generalized linear phase systems, in particular FIR systems. So in particular, generalized linear phase, FIR. If you're not sick of letters, sick of capital letters already, there's a big dose. So generalized linear phase FIR systems, and what I mean by that, there's a whole theory of these. Like a GLP FIR system, the frequency, the impulse response H of n has to have certain symmetries, and there's 4 types. So of these, there are 4 types. And guess what they're called? Okay, this is great. So imaginative. They're called Type 1, Type 2, Type 3, and Type 4 GLP FIR systems. Okay, so anyway, I apologize. There are 4 types, and in each type features a certain symmetry in the system's impulse response. H of n, like for example, it could have an even number of taps, even length, odd symmetry, odd length, odd symmetry, even length, even symmetry, all that kind of thing. Those are the 4 different types of FIR systems that have generalized linear phase. And furthermore, you get a kind of an intuition for what's going on with these things by looking at the form of H hat of omega hat. That essentially, when you put a pure sinusoid through a GLP system, so furthermore, the quote-unquote action of a GLP system on sinusoids, on a sinusoid, is sort of like multiplication by a constant followed by a delay. So what do I mean by that? And the book goes into a lot of, well, not a lot, but some depth on this matter. And I'm not going to go so much into this in class. I'm going to put it in that long promised handout, the one that covers the pesky boundary case and all that kind of thing. But how does this work? Here's the idea. Suppose you drive a system that has a generalized linear phase frequency response. Suppose, just to be specific, say H hat of omega hat is equal to some function A of omega hat times times, how about e to the minus j3 omega hat? That's a possibility. So the alpha up there is equal to 3, the beta is 0, and a of omega hat is anything. What happens when I put in something like this? What happens when I put in, say, cosine of n omega 0 hat plus phi into this system? What comes out? Well, remember what the frequency response describes. First off, it describes the way systems respond to pure sinusoids. The magnitude of the frequency response at the frequency omega 0 hat is the factor by which the system changes the amplitude, and the phase is the factor by which it changes the phase. So this comes out to be the following. A of omega 0 hat times cosine of n minus 3 omega 0 hat plus phi. So what happens here is that the amplitude gets multiplied by a of omega 0 hat, and the time gets shifted by whatever this thing multiplying omega hat is up here. And usually it's an integer, sometimes it's a half integer. We have to be careful. You can check this for yourself. Okay, so that's the way the system acts on sinusoids. It decomposes into multiplication by a constant, so here's the constant, followed by a delay. Okay, so that's the idea in one specific example. And I'm not going to talk in any more depth about this in class, more on this in a handout. And suffice it to say that generalized linear phase systems are good. Like in digital signal processing, one of the goals is to develop a system that does the job you want it to do, but that also has generalized linear phase, because then we know that the phase doesn't mess it up too much. Okay, so one general comment is that in DSP, you often want to design systems that do whatever job they have to do system-wise, and generally that's going to be some filtering, like filtering out certain frequencies, whatever, that do what they do system-wise, or what they're required to do system-wise, and have generalized linear phase. So that's one thing. You can take that to the bank. Like, you can impress your friends with that kind of general comment. Jack. I'm talking to see you, Air Jack. I know there's another Jack over here, but yeah, it's because the question is, why do you want to have the system have generalized linear phase? It turns out that phase is the thing that messes you up. Phase messes you up. Like when we talk about ideal low-pass filters in a bit, all right, we're gonna talk about the fact that you can't build an ideal low-pass filter because it's not a causal system. But you can build filters that are not ideal low-pass filters. And what's non-ideal about them is they have phase. And what that means is that the system messes up signals that have complicated frequency content. And I guess that's a little bit too sophisticated for now. We'll get to that as we go along. All right. Okay, so there's a couple more things I want to wrap up from Chapter 6 before we move on to the material in Chapter 7. All right? So here's a couple of loose ends. All right. First off, I promised you that I would tell you why people refer to what we looked at earlier as a low-pass filter, and why they refer to what we looked at as a high-pass filter as a high-pass filter. So where whence comes the quote-unquote low-pass and high-pass terminology. And last semester I asked the same question in another context. I think it was for Fourier coefficients. And someone said, what do you mean by whence? And I said, whence just means from where. And the person said, this is not a Shakespeare class. We're not supposed to know that. Well, I think you should know that. I think you should know that whence means from where. Does anyone know what to where mean? What the word for to where is? Where to? This is not obscure. Okay. Whence cometh low-pass, high-pass terminology? All right. Whither are we going with this? That's the word. Whence and whither. Okay, so you learned some Shakespeare. All right. So anyway, whence comes the low-pass, high-pass terminology? Well, here's the idea. The idea is that frequencies, and I want to be really specific here, so omega hat values, normalized frequency, omega hat values near 0 correspond in some sense to low frequency, and omega hat values near pi correspond to high frequencies. Okay, you say, okay, he's telling me that that's why that correspondence holds. Why does that correspondence hold? Why do we think of these things near 0 as being low and things near pi being high? Well, the background thing, the thought that's going on in the back of people's mind. So the background sort of story here is that in real life, what we've done is we've decided we want to process a bunch of continuous time signals, but we want to use discrete time systems. So first what we have to do is sample the continuous time signals. Then we process their sampled versions. So want to process continuous time signals all of which have some common bandwidth F max. And you can make it the common bandwidth just by taking it being the biggest bandwidth of all of them. Okay. And we want to use discrete time systems. Because those are cool. All right. So what do we do? What do we do? We sample the continuous time signals. We sample the continuous time signals faster than their common Nyquist rate. So we sample all of them faster than their common Nyquist rate. So the sampling frequency f sub s is going to be bigger than 2f max. All right? So in continuous time frequency space, the signals spectra, that's signals apostrophe, that's plural possessive, spectra are confined to the interval minus f max less than or equal to f less than or equal to f max. So schematically, it looks like this. Here's f space, here's 0, and here's f max, and here's going to be fs. Here's minus f max, and here's like minus fs. So all the spectral activity is in here. Okay? Now, when we sample at frequency fs, what this does is it gives us discrete time signals whose spectra look like this. They look like this on minus pi pi in omega hat space. So this is going to be pi, and this is going to be minus pi. And when you do the scaling on the frequency axis, fs over 2 goes to this when you do the transformation, and minus fs over 2 goes to this. And here is going to be plus and minus omega max hat. So this is minus omega max hat, omega hat max. I don't know how you want to say it. And all the activity is in between those two. And there's nothing between omega hat max and pi. So there's nothing here. And what is omega hat max in terms of f max? What is the substitution that takes f to omega hat when you sample? It's 2 pi fts equals omega hat. I have to go through this every time by hand. So what is omega hat max? Because we have 2 pi fts equals omega hat, what that means is 2 pi f max Ts is equal to omega hat max. So that's how you figure out omega hat max. But in any event, in continuous time frequency space, anything out here, at least with respect to the set of signals we're talking about, is going to be high frequency, relatively high frequency. So anything out near f max or higher. So for these signals in continuous time, anything near or above f max is high frequency. And anything near 0 is low frequency. And in discrete time, having sampled them, because f max maps to omega hat max and fs over 2 maps to pi, so in discrete time, so this here is fs over 2 and minus fs over 2. Since fs over 2 maps to pi and f max maps to omega hat max, omega hat values near or above omega hat max that is to say near pi, omega hat equals pi, are quote-unquote high frequencies. And so that's why that correspondence, omega hat values near 0, low frequency, that's pretty natural seeming, and omega hat values near pi, high frequency, that's how it comes about, because of this sort of background view of what's going on, that the original objective was to process continuous time signals, and we sampled them faster than Nyquist rates, and we got discrete time signals whose spectra were confined in between two values to the left and the right of pi and negative pi, respectively. Okay, so whence comes low-pass, high-pass terminology? From there. And just to remind you what the frequency responses of the low and the high-pass filters that we looked at earlier were, or at least the magnitudes. So recall that we had for h hat of omega hat for the high and low pass filters were respectively this for the high pass, and remember we only ever graph it on minus pi to pi because it's 2 pi periodic, and this was 2, and this for the low pass. Comes at slope 0, goes up to 4. So, how does this correspond to high passness and low pass? Well, if we think of the high frequencies as the ones out here and the low frequencies as the ones in here, you could see that this guy, the high pass filter, attenuates the low frequencies and doesn't attenuate the high frequencies as much. It passes them better. So it passes higher frequencies better than lower ones. And this one, other way around. When you're out near pi, that is to say when you're at high frequency, this system tends to attenuate. When you're near 0, it tends to pass or amplify even. Okay? So there's some justification for the high and low pass terminology. Another little loose end. So this will be item 2 in our list. Is frequency response of the cascade of 2 LPI systems, of two FIR systems. What does LPI stand for? LPI? On my car, I have a sticker LBI because that's where we go, and Alec knows what I'm talking about, that we go to the shore, the Jersey Shore, Long Beach Island every summer. And so I have an LBI sticker on my car that doesn't have Long Beach Island written on it, so you have to know what it means. You know, it's a much cooler kind of sticker that way. But I can't think of what LPI would be. Long Peach Island? In Georgia? No. Anyway, LTI, FIR, I get confused. So what do we do? What happens when we cascade 2 systems? What happens to the frequency response? What is the overall system's frequency response? So here you got your 2 systems. System 1, and I'll represent the fact that it has a frequency response by putting H1 hat of omega hat inside its box. And then we send that to system 2 that has frequency response H2 hat of omega hat, and that's the output. So what is the overall system's frequency response? What do you think it is? Anybody want to just guess? Maybe you know this already from circuits. Nobody? Nobody? Alicia? Yes, that's correct. It's the product. Now why? You have to tell me why. Why do you think it's the product? Why do you think it's the product? See, it doesn't really matter if you can give me a good reason or not, because this is sort of what it has to be. You know, everything comes out nice, right? And so what's going to happen when you cascade 2 systems? The frequency response has got to come out to be something nice, and we don't know how to do anything with functions of omega hat except like multiply them or add them or whatever. And it seems pretty natural to. So don't worry, you don't have to know why. Okay. I want to prove this, quote unquote prove, by using the picture method for frequency responses. Okay, so you prove this really easily using, quote unquote, using the picture. Remember last time I said I'm going to refer to this, if I remember, as using the picture. What is the picture? The picture says e to the j n omega hat goes in to a system. What comes out is h hat of omega hat times e to the j n omega hat. So let's use the picture on this picture. So we put in e to the j n omega hat to system 1, first system, the one that has h1 hat of omega hat. What signal is in this middle arrow? Okay, other Jack. Yes. It's h1 hat of omega hat e to the j n omega hat. By that picture applied to this first system. Now we put this through the second system. The h1 hat of omega hat acts just like a number, okay? It doesn't depend on n. So what comes out of this is going to be h1 hat of omega hat times h2 hat of omega hat e to the j n omega hat. Thus, for the overall system, when we put e to the j n omega hat into it, what comes out is h1 hat of omega hat, h2 hat of omega hat, e to the j n omega hat, and therefore this, whatever multiplies e to the j n omega hat over here, has got to be h hat of omega hat. So, cascade systems multiply frequency responses. Very good. Okay. Did everybody buy that? I hope so. And by the way, remember what happens to the impulse responses when we cascade two systems? Yes, they get convolved. And it turns out this is going to have to do with DTFTs. That'll be the topic of at least the second part of this class, if we get there. Okay, so now I want to think about another loose end here from chapter 6. Is a kind of a design problem. I know I'm being a little artificial by calling this a design problem, glorifying it as a design problem. It's not really, it's not really a complicated design problem per se. But here's the deal. And now I'm looking for chalk. By the way, remember I told you last time that they're running out of chalk in this room? Well, I went to 205 Thurston, and in the cabinet, like that one up there, they had a whole bunch of these boxes of chalk. So I stole one, all right? And actually borrowed it. I'm going to put it back when this is all over. But anyway, I have a stock of chalk in case they actually run out in this room. I took two pieces out of my box to start with. So, another thing. Now let's consider a design problem of sorts. Okay, so what do we want to do? We want to design a causal FIR system that kills a cosine. So we want to design a causal FIR system as simple as possible, a system that kills all cosines of a given frequency, kills all discrete time sinusoids of a given normalized frequency omega 0 hat. Okay? Now, why would you want to do that? Well, you probably can't hear this, but in this room right now, there's this really annoying kind of rotating machinery type of hum coming from up in this general zone. And I really wish I weren't hearing that right now. So I really wish I had a causal FIR system, like hanging between me and that vent or whatever it is, that killed that cosine. And you know, you've probably walked into rooms where there were old fluorescent lights that were like humming away at 60 hertz, and it was, you know, okay, so that's the kind of thing. You want sometimes to kill signals of a certain frequency for whatever reason. Okay, so we want the system to be something that takes anything in the form a cosine n omega 0 hat plus phi and puts out the 0 signal. And here omega 0 is given. Omega 0 hat is given ahead of time. So it's a specific frequency you want to kill. All right. So how do we go about doing that? What do we need to do? What is our job in terms of the frequency response of that system? Okay. Now we have to think, what does frequency response tell us? It tells us all about the system. We know that from last time, but when we first introduced frequency response, where did it come from? It came from analyzing how the system responds to pure sinusoids. And the frequency response reflects that directly. Okay, so in terms of frequency response, what do we need? We need to design the system so its frequency response h hat of omega hat satisfies what identity? I needed to kill every cosine of every sinusoid of frequency omega 0 hat. What does h hat of omega hat have to, what property does it have to have? H hat of omega hat equals 0? That's the 0 system. Yes, h hat of omega 0 hat equals 0. Okay? Any system that has this property kills all the sinusoids of frequency omega 0 hat. Got that? All right, so before I move on with this example, let me refer back to the examples from the last lecture. So this is a sort of a parenthetical comment. Here's an aside. Okay. We had, for the high-pass filter, h hat of omega hat is equal to 2 sine omega hat over 2 times e to the minus whatever something, j something. This thing is 0 at omega hat equals 0. So that means that h hat of 0 equals 0, which implies that the system kills 0 frequency sinusoids. And what are those sinusoids? Those are the constant signals, right? This system kills all the constant signals. If you put a constant signal into the system, you get the 0 signal out. And an ECE, the fancy ECE way of saying that is that a quote-unquote a high-pass filter kills DC, because DC is like a constant signal. So high-pass filter kills DC. Okay, now what about the L-fold running averager? So as for the L-fold running averager, or running summer, running, I cannot spell that word. Isn't that weird? I always forget that third N. L-fold running summer, we had this. We had that H hat of omega hat is equal to DL of omega hat. That was the Dirichlet thing, the periodic sinc function. We drew all kinds of pictures last time, times e to the minus j L minus 1 over 2 omega hat. Okay. And when L was 5, we found that D5 of a couple of very specific values of omega hat were 0. D5 of plus and minus 2/5 pi and 4/5 pi are 0. Thus, this system kills sinusoids of frequency 2 pi over 5. So omega 0 hat equals 2 pi over 5 and 4 pi over 5. Okay, so those are examples of H hat of omega 0 hat being 0 for specific values of omega 0 hat. Okay. So anyway, back to our problem. We're given omega 0 hat. We want to design a system, a causal FIR system, as simple as possible that kills all the discrete time sinusoids of some specific frequency omega 0 hat that we have ahead of it. How do we do that? Okay, well, let's address the as simple as possible requirement. And now is a good time to take a 3-minute break. And I'm not going to take a full 3 minutes because that's really awkward when you're standing in an empty room to stare at seats for 3 minutes. But it's good for me to relax a little bit, you know. Jack, what was your question? Yes. As a matter of fact, this is my second lecture of the day. I gave a lecture earlier today, around noon, and now I'm back here at night giving this lecture. And actually, I don't think I've ever given 2 lectures in one day before. This might be a first. But I already told you why. I already told you what we're up against here. So anyway. So let's make some conversation. How are you guys doing? Where are you? Let me know. Keep in touch. Chime in on Piazza. Kyle, you're the one who always looks like you don't quite believe what I'm telling you, but you have sort of a half smile on your face. I remember that person I talked about last time. That was you. Okay, so just in case. And Hannah, I've been wondering, did you ever find weren't you the one who lost your AirPods in class, and they were in the case, but they weren't there when you came back and looked for them? And did you ever find those? Okay. Well, anyway. Maybe we'll figure out a way for people to get extra credit if they find all the little trivial shout-outs to them in lecture videos. That would be fun. Little Easter egg hunt. It's that time of year. How about that? All right. So anyway, end of 3-minute break. So let's see how we can solve our problem. So what is as simple as possible mean? That's going to mean that M is as small as possible when the system obeys this difference equation. So y of n is equal to, say, sum from k equals 0 to cap m, bk x of n minus k. So in some sense, it's the smallest length filter. It's the fewest number of taps. That's what we mean by as simple as possible. Okay. So what about the n equals 0, right? The general form of the system is going to be y of n is equal to b0 x of n. Now, clearly, you can trivially choose b0 equal to 0, and this becomes the 0 system. And that will kill any cosine of any frequency, including one of some pre-specified frequency omega 0 hat. So trivially, setting b0 equals 0 gives you a system that kills every sinusoid, including those of frequency omega 0 hat. So omega 0 hat ones. And so this is not what we're looking for. Okay. So what about m equals 1? How about that? Can we build a system that's not trivial, m equals 1, that kills sinusoids of frequency omega 0 hat, where omega 0 hat is pre-specified. So m equals 1. The most general form of such a system is going to be this. Y of n is equal to b0 x of n plus b1 x of n minus 1. Okay, now we don't want the trivial answer, so we want to ignore the trivial answer. Namely the 0 system, setting both coefficients equal to 0. System's frequency response is h hat of omega hat is equal to b0 plus b1 e to the minus j omega hat. Okay? You can figure that out using either the formula with b's or the picture, whatever. Now, what does it mean if we want to set, we want h hat of omega 0 hat equal to 0, that's true if and only if b0 plus b1 e to the minus j omega 0 hat equals 0. Okay? Now, b0 is real, right? So is b1. So for that to be true, what has to be true? E to the minus j omega 0 hat must be real. So must, therefore, be real. And so what does omega 0 hat have to be? It has to be a multiple of pi. It could be 0, it could be pi, it could be 2 pi, it could be 3 pi, it could be whatever. So hence we need omega 0 hat to be equal to an integer multiple of pi for this to be doable. For an m equals 1 system to do what we want to do the job of killing cosines, killing sinusoids of frequency omega 0 hat. And by the way, the high-pass filter was an example of such a system for omega 0 hat equal to 0, because we had 1 and minus 1. Those are the things that work there. And anyway, okay, so let's look at m equals 2. Let's see if we can kill more general sinusoids with an m equals 2 system. And it turns out we're going to be able to kill any specific sinusoid, any pre-specified sinusoid by designing the Ds correctly. So it turns out we can design an n equals 2 system to kill any specific pre-specified omega 0 hat. How do we do that? What is the general form of the system? Y of n is equal to b0 plus b1, or sorry, b0 x of n plus b1 x of n minus 1 plus b2 x of n minus 2. H hat of omega hat you can calculate to be b0 plus b1 e to the minus j omega hat plus b2 e to the minus 2 j omega hat. Right? Now, I claim we can design b0 and b1 and b2 given omega 0 hat so that h hat of omega 0 hat is 0. How are we going to do that? And here's where I sort of have to look at the page, because I have a cute way of doing it and an ugly way of doing it. So let me just see which way I want to use. Cute or ugly? Ugly. I am really afraid that the thing is, if I knew how to pause the video, here's what I would do. I would say, I want to go get a drink of water, and I'd pause the video, and instead of getting a drink of water, I'd sit down and work it out. But actually, I am thirsty, so I'm going to see if there's a water fountain nearby. If there is, I'm going to get a drink of water. Right back. I did get a drink of water down the hall, but while I was there, I decided to do it the cute way instead of the ugly way. So, how are we going to do this? So, what we want to do is we want to design B0, B1, and B2 so that H hat of omega 0 hat, which is B0 plus B1 e to the minus j omega 0 hat, plus b2 e to the minus 2 j omega 0 hat equals 0. So how are we going to do that? Well, here's one way to do it. Haha. Pretending I just thought of this. Let's manipulate this kind of the same way we did the example frequency responses last time. So we're going to factor an e to the minus j omega 0 hat out of that whole expression. And we get this, b0 e to the j omega 0 hat plus b1 plus b2 e to the minus j omega 0 hat times e to the minus j omega 0 hat is equal to 0. Now this guy is never 0, so we can just cancel that. And now let's play with what's in here. See if we can pick B0, B1, and B2 to make things work out nicely. Well, B1's got to be real. So we have to pick B0 and B2 so that the sum of the B0 term and the B2 term is real. And what's an obvious way to do that? Picking B0 and B2 to be equal to each other maybe even equal to 1. So if we set B0 equals B2 equals 1, you get this. E to the j omega 0 hat plus B1 plus e to the minus j omega 0 hat. E to the minus j omega 0 hat is equal to 0. Now, these two terms pair up Euler-wise to give us 2 cos omega 0 hat plus B1 e to the minus j omega 0 hat is equal to 0. And that makes it obvious the choice of B1 to make things work. B1 equals minus 2 cos omega 0 hat. Conclusion. Amazing what a trip to the water fountain will do. Oh, you know what? Cornell's being nice about parking, so like I could actually drive my car to campus and park, which I can't usually do because I live walking distance and I don't even have a permit or anything. But my car is for the first. I've worked here for like over 38 years now, and I don't think I've ever parked in the lot over here behind like Thurston in my whole life, and my car's over there now, and it's like, wow, I feel important. Frank Rhodes used to have 3 spaces over there because he had 3 different license plates. I don't know, it's crazy, but he was a geology professor before and after he was president. But the bottom line here, here's a system that works. For any omega 0 hat, the causal FIR system covered by this difference equation, y of n is equal to x of n minus 2 cosine omega 0 hat times x of n minus 1. That's a number, by the way, plus x of n minus 2 kills every cosine of frequency omega 0 hat. It has h hat of omega 0 hat equals 0, and thus. And is the word kill a little bit too violent for us? Do we want to say something else? How many use the word annihilates? Because that's another word. Some people think annihilate is more violent than kill, but I think kill is more violent than annihilate. Because you can annihilate something that's inanimate, but you can only kill something that's animate, right? So, and thus annihilates any sinusoid of frequency omega 0 hat. So that's a solution to our design problem, as it were. We wanted to design a system that's as simple as possible that kills every cosine of certain frequency that's pre-specified. And we found that we couldn't do it with a m equals 1 system unless it was a very special kind of sinusoid. Omega 0 hat equals 0 or pi, whatever. But we found that with a second order system or a third order system, whatever you want to call this, the one where m equals 2, we can get a system of that complexity, that low complexity, that kills every cosine of a pre-specified frequency omega 0 hat. Okay. So let's build on this just a little bit. So what if not only do we have an annoying fan noise and an annoying, say, 60-cycle hum from an old fluorescent light, but we also have someone who just has, earbuds in and is not conscious of anyone else's presence, is constantly whistling at some frequency, and we want to kill that too. Whatever. We want to kill multiple frequencies. So here's a sort of a more general problem. Say you have, how about omega 1 hat, omega 2 hat, and omega 3 hat, and maybe out to omega, say, L hat are frequencies, all of which you want to kill. So these are given, so they're distinct given frequencies, how might we design, how might we build a causal FIR system that annihilates cosines of any of those frequencies? So annihilates any cosine of one of these frequencies. Okay, so you don't just want to kill one frequency, you want to kill, say, 2 or 3 or 7 or 13 frequencies. And you don't want a trivial answer. You don't want to build a zero system. That's out of the question. How might we do this? Okay. Anybody have a suggestion? Okay. Okay. Well, let me give you a hint. Recall that if we have two systems and we cascade them like so, the overall system has this as its frequency response. The product of two individual ones. Now, does anyone have an idea of what to do? Alicia, you already answered her question, but I'll let you answer another one. Yeah, exactly. You design the first system to kill the first frequency cosines, the second system to kill the second frequency cosines, and so on. And because these frequency responses multiply, the overall system, cascading L of those systems together, annihilates all these frequencies. So the solution to our problem is for each k, let hk hat of omega hat be the frequency response of an quote-unquote m equals 2 system that annihilates cosines of frequency omega k hat. And I'll abbreviate that just by saying omega k hat, i.e. hk hat of omega hat is going to equal 1 plus 2 cosine omega k hat, or sorry, 1 minus 2 cosine omega k hat e to the minus j omega hat plus e to the minus j2 omega hat. That's the frequency response of the system that we just designed that annihilates frequency omega k hat. Then the product, then cascade them in order, so form the overall system by cascading all these. So first system, second system, and so on down the line. The overall frequency response is going to be the product of all those, and by virtue of that fact, the overall system annihilates all the frequencies that we want to annihilate. Right? Because if you put in an omega k cosine into that system, it'll go through all of them until it gets to the kth one, and then that'll annihilate it. So then you'll annihilate the omega hat k. You do that, and that'll do it for every single one of these, omega hat 1 through omega hat L. So since the overall frequency response is this product, h hat of omega hat equals h1 hat of omega hat dot 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 times hl hat of omega hat. Put one more factor in there for good measure. We have that h hat of omega hat k is equal to 0 for 1 less than or equal to k less than or equal to L, and we're done. Okay? That solves our problem. Everybody see that? Because if I plug in omega hat k for omega hat in h hat of omega hat, it goes in here in each of these, and the kth one is going to be a 0. So boom, that makes the result 0 for 1 less than or equal to k less than or equal to L. Okay, question, how complicated is this system? In the sense of how big is its M? How complicated? What's the order of the system? Each of the component systems, right, has an M equals 2, has an impulse response that has 3 terms in it. All right? So, question. How complicated is this system? Like, how complicated a system do you need to kill L cosines, annihilate, if you will, L cosines simultaneously? So that is, what is its M? When you write the system this way, y of n is equal to sum from, well, let's not even do that, because that'll confuse you with k's. All right, what is its M value? Well, each component system has an impulse response that has 3 non-zero terms in it. So note that each component system has an impulse response h of n. So you're going to have h1 of n, h2 of n, h3 of n. Those are the impulse responses of the respective component systems. Has impulse response with duration interval (0 less than or equal to n less than or equal to 1). Okay, so the duration interval of each of these guys is going to have length 3. And what do we know about impulse response of cascaded systems? If you cascade systems, the frequency responses multiply, but what do the impulse responses do? Who said that? Eric. Yes, they convolve. So, cascade systems, this is something we discovered 2 lectures ago. That corresponds with convolving impulse responses. So, and when you convolve 2 finite durations